Does finding the shortest distance from a point to a subspace guarantee exactly one closest point? In classical geometry, the answer is yes. We imagine a sphere expanding outward until it barely grazes a flat plane at exactly one coordinate. But outside of classical spaces, this intuition breaks. If we change how distance itself is measured, our expanding distance shape might be an angular octahedron. When the shape meets a plane, a flat edge smashes flush against it, creating an infinite line of simultaneous contact points. To understand why this happens, we have to examine the physical geometry of Banach spaces. We need to see how the mathematical definition of a space determines whether a unique closest point can even exist. The property acting as the filter between these two realities, the single point versus the infinite line, is strict convexity. Knowing the topological distance to a subspace does not yield a unique solution on its own. The actual geometry of the space's unit sphere dictates whether ambiguity is physically possible. Let's establish the baseline. This diagram shows a standard 3D Euclidean space. We have a target point x0, and our subspace y is the flat plane at z equals 0. To find the best approximation of x0 in y, we drop a perpendicular line to the plane. That single coordinate minimizes the distance, and that distance delta is simply the absolute value of the z-coordinate. Now we shift the grid to a flat 2D plane and change our measurement tool to the L1 norm. This equation defines distance as the sum of the absolute values of the coordinates. We plot our point x at 1, -1. Our subspace y is the diagonal line where the x and y coordinates are equal. We want to find the shortest distance between our point x and any point y on that diagonal line. Plugging our coordinates into the L1 formula gives us this equation. Pulling the negative out of the second term, this simplifies to the absolute value of 1 minus eta plus the absolute value of 1 plus eta. If we pick any value for eta between -1 and 1, the total sum of this equation is exactly 2. Visually, as the L1 distance grows, it forms an expanding diamond. When the distance reaches 2, the diamond's flat upper left edge perfectly aligns with the diagonal line y. Because an entire edge of the L1 diamond touches the subspace simultaneously, every single coordinate on that segment is exactly a distance of 2 away. We have generated infinitely many best approximations. This visual anomaly is governed by convexity. A set is convex if you can take any 2 points inside it, connect them with a straight line segment, and that line remains entirely inside the set. The shape on the left is convex. In the crescent shape on the right, the line breaks the boundary, meaning it is non-convex. Lemma 6.2-1 formalizes this geometry. The set of best approximations to a point x out of a subspace y is always a convex set. Let's assume our set of best approximations has at least 2 distinct points, y and z. This diagram shows our target point x surrounded by a boundary sphere representing the minimum distance, delta. Both y and z sit exactly on this boundary. We then select an arbitrary point w located anywhere on the straight line segment connecting y and z. When we apply the triangle inequality to measure the distance from x to w, the math restricts the length. The distance is bounded by the weighted average of the distances to y and z. Since both of those are exactly delta, the distance to w must also be exactly delta. This proves that if a space allows multiple closest points, those points must form a completely flat line segment that rests perfectly flush on the surface of the distance sphere. To guarantee uniqueness, the space's unit sphere must ban straight line segments entirely. This brings us to definition 6.2-2. Strict convexity. A space is strictly convex if for any 2 distinct vectors of length 1, the norm of their sum is strictly less than 2. The standard triangle inequality states that this sum is less than or equal to 2. Strict convexity deletes the equals option. Visually, look at a perfectly round circle. If you pick 2 points on the boundary and add them, the midpoint between them pulls away from the edge. It falls strictly into the interior. This yields theorem 6.2-3. In a strictly convex normed space, there is at most one best approximation to x out of a given subspace. Strictly convex spaces physically cannot support the flat line segment of solutions we mapped out in the previous lemma. The distance sphere is rigidly curved, meaning it can only touch a subspace at one point. We can test which major spaces actually possess strict convexity using lemma 6.2-4. Part A of the lemma proves that Hilbert spaces are strictly convex, relying directly on the parallelogram equality. If we take two distinct vectors, x and y, of norm 1, separated by some distance alpha, we can substitute those values into the equation. It simplifies to the norm of x plus y squared equals 4 minus alpha squared. Since alpha squared is a positive number, the result is strictly less than 4, proving the norm of x plus y is strictly less than 2. Part B shows that CAB spaces lack strict convexity. This graph plots two continuous functions on the interval a to b. x1 is a flat horizontal line at 1. x2 is a diagonal line. Both functions have a max norm exactly equal to 1. When we add these functions together, the maximum absolute value of the combined function equals exactly 2. The inequality is not strict. This leads to theorem 6.2-5. For any x in a Hilbert space and any closed subspace y, there is always a unique best approximation. Hilbert spaces inherit strict convexity from their inner product structure, making them perfectly behaved for approximation. CAB spaces, governed by the max norm, are geometrically flat and inherently prone to infinite solutions. Finding a closest point requires completeness, but as this split screen demonstrates, ensuring it is the only closest point requires strict geometric rigidity. If a space allows multiple best approximations, they will always form a flat line on the surface of the distance ball. Hilbert spaces are the standard for approximation theory, precisely because their inner product geometry outlaws these flat edges. If we want to do uniform approximation in a flat space like C, A, B, the geometry of the unit sphere will not protect us from ambiguity. We need entirely different mathematical machinery to force uniqueness. Mathematical guarantees of uniqueness are never free. They are paid for by the inherent geometric curvature of the space itself. When that geometry fails us, we have to impose new conditions, setting the stage for Haar conditions.